Hi, my name is Xiangrui. So I'm a software engineer from Databricks. And today I'm going to share some experience from scaling up the recommendation algorithm in MLlib. So the purpose is, one is for developers to help developers to understand the MLlib algorithm implementation. And the other one is to just get some ideas. People can apply those ideas to other ML algorithms and make them faster and make them more scalable. And before my talk, I just want to mention a talk in parallel downstairs. So Drew Yun from MyFitnessPal is talking about a good recommendation application. They are doing recommendation on food and recipes. So if you are more interested in application than the implementation, well, maybe you should go to that talk. But if you want to leave before you go, the TLDR for my talk is we can scale up to 100 billion ratings. And yeah, let's start. I'm from Databricks, and maybe everyone here already know that, but this is funded by the creators of Spark. And we are contributing to make the major driving force to the open source Spark. We have our own hosted platform called Databricks, and sitting on top of Apache Spark and provided end-to-end solutions. And you can sign up today, right now, at our company's website. Since there is no general MLlib talk in this Spark Summit, I want to spend a couple minutes on just to give a brief review of MLlib. So the initial contribution for MLlib was from MLlib, the same place they built Spark. And MLlib shipped with Spark since version 0.8. That was maybe September of 2013. And currently, we have more than 50 organizations and 150 individual contributors contributing to MLlib. So it's a very popular machine learning, open source machine learning project. We have a good coverage of algorithms. And you can just either check our website or just open a machine learning textbook. That's about the same list. And for our mission is really to make practical machine learning scalable and easy to use. The first one is we try to make our API really user-friendly, and then they can build machine learning applications quickly as part of their daily workflow. Second thing is we really want to speed up our machine learning implementation for large-scale data sets. And Joseph yesterday already talked about the pipeline API. That's basically the effort we made to make machine learning easy. And then today, I want to talk about a little bit, dive into the implementation and show we spent really a lot of time and effort to scale up the implementation in MLlib. Let's start with a brief history of MLlib. So the initial version of MLlib is 0.8. And the same as other machine learning libraries, we include a basic selection of algorithms, like linear algorithms, k-means, and ALS, the alternating least squares, and today I'm going to talk about. So initial version has Java and Scala API. And after 3 months, we added some more algorithms, and that include the implicit preference for alternating least squares. Basically, if you don't know, well, explicitly whether this user is giving a 5-star rating on this product or not, it's just based on some implicit activity, and then you should use this implicit preference for a recommendation. And we also added Python API in this release. And then in 1.0, and we added a bunch of distributed linear algebra methods like PCA, SVD, and people can use that to do feature projection and do all kinds of feature engineering. And we also add LBFGS to scale up the linear algorithms. And then in 1.1, we added another statistics library and some streaming integration for online machine learning algorithms. And in this release, we also added non-negative matrix factorization. And basically, you say, why in my prediction I saw some negative ratings? Well, user will never give negative ratings because they can only give 0 or 1. So then I want to put a constraint. In my prediction, I don't want to see negatives. So that's this non-negative matrix factorization. And then in 1.2, well, the major effort was on the pipeline API. That was the first release for the pipeline API. We tried to make make the API really user-friendly. And on the algorithm side, we added a bunch of tree ensemble methods, like random forest, gradient booster trees. Then in 1.3, actually, it was a boost of machine learning algorithms. And besides the machine learning algorithms we included in the MLlib repository, we also added a Spark package website. And basically, we know that in real world, people want to customize their machine learning algorithm for their particular specific applications. And we cannot easily maintain all those modifications inside a single repository. So we built this third-party index to allow people to submit their own implementation to this website, and then users can find whether they have some existing application that can fit their use cases. So basically, this is a third-party index for the entire ecosystem. And in this release, we bumped the ALS implementation, and basically this is the main content of this talk. And see how we scale up the ALS implementation in MLlib. And now in 1.4, well, we just another boost on the pipeline API. We added a bunch of feature transformers. And the Python API is now almost on par with the Scala API. So Python users can easily use those the pipeline API to build their own machine learning pipelines. And for the recommendation, we added a method in ALS called recommend all, just basically give me all the users. Let's see, give me all the top K recommendations for all users. OK, that's a brief history of MLlib. And you can go to the website and see more detailed user guide of MLlib. And let's jump to this recommendation algorithm called alternating list squares. So basically, it's a collaborative filtering algorithm. And for recommendation, usually the input is some rating matrix. And this is a rating matrix of 9 by 9 rows and 9 columns. And each row represents a user, and each column represents an item. And basically, each element in this matrix means a rating from this user to that item. And the recommendation problem is, in the middle cell, I put a question mark. And the recommendation problem is, can you give me a good estimate of what value it should be for this position? Basically, I'm asking how likely this user will rate this item, maybe 5-star, 4-star. So based on that, I can make a recommendation. And you may already discover this is not a rating matrix. This is a Sudoku. So basically, yes. If this is a Sudoku, and if you spend hours on it, this is a really hard Sudoku question. And you know, well, we should fill in 9 in that question mark. But why we know what to fill in? Because for Sudoku, you know there's a strong restriction on what numbers you can put. They put specific rules on the numbers you can put. So then, well, each rule you added, you reduce the degree of freedom of the problem. And in the end, you only just have 1 degree of freedom. So for recommendation problem, it's about the same. If I told you that there's no correlation between those ratings, and all the ratings are independent, there's no way you can tell, well, what the value you should put in the question mark. And so we need to make some assumption on the input data such that, well, we can reduce the degree of freedoms and so make a good estimation of the ratings. And this assumption in the algorithm is called low rank assumption. It's a rating matrix, and we assume that the matrix is low rank. But I will tell you why. Basically, if I ask you some question like, what kind of movies do you like? You won't give me a whole list of your favorite movies. Maybe you just talk about, OK, I like sci-fi movies. I like crime, action. Right? So usually your description is based on some latent space. You don't talk the movies directly. You describe your preference. And this latent space can be represented by just a low-rank factorization of the matrix. Basically, you put your preference to a lower dimensional space, and you map the movies you like to the same space. Basically, I like sci-fi, I check that place. And then if a movie is a sci-fi movie, I put a check there. And then I count how many matches I have. Then I can have a good estimate of how likely I will love that movie or not. And this assumption is basically the rating matrix can be decomposed into a two low-rank matrix. I put A here, and it's approximated by U times V transpose. And UV are all tall and skinny matrix, representing the user preferences and movie preferences on the latent space. And then the question is how to estimate U and V. And basically, if I say, I like colored movies, so you don't get any information from me, right? So basically, that's all movies right now. Maybe just except one or two movies. And basically, we need to define something and to let machine know how to optimize. And machine doesn't understand those preferences. And we need to give the machine a very numerical objective function to optimize. And this is the reconstruction error. And basically, we want to minimize the Frobenius norm of the reconstruction. That's A minus U transpose V. And Frobenius norm, we just take all the elements and take the sum squares. And however, well, you know that A is the rating matrix, and it's very sparse. And basically, there are a lot of unobserved ratings in the input matrix. We cannot just calculate that directly. For that one, so the solution is we only check the observed ratings. So it's just a subset of the first formulation. I use that as the reconstruction error. That's the objective function of this ARS problem. However, this problem is not that friendly because it's not convex. If you don't understand convex, basically you can translate it into easy. It's not easy. However, if we have the unknowns are the matrix U and the matrix V. If we fix one, for example, U, and we found that objective becomes really nice and friendly, it becomes convex and separable. And for example, I can say, if I fix U, that means we fix the user preference. I want to solve for item preference. And I can express the objective as a sum on the items. And for each item, it's a small subproblem. And this subproblem is a least square problem. And that's why, we call it alternating least squares in the algorithm name. And we can solve those subproblems in parallel. And each one is a really small least square problem depending on the rank you set. The rank is basically you have the low rank assumption, and you say, well, the matrix should be rank 20 or rank 10, and based on your data. So now we can do this to optimize the optimization problem. We can first fix U and solve for V, and then fix V, solve for U. And that's why it's called alternating directions. Basically, you take this step and take that step, take the step back, and then until it converges. And usually, it converges really well for real-world data sets. And for the complexity analysis, and usually if we solve a least square problem of size n by k, and that needs n k square. And so then, to solve the the entire least square subproblems, we need the number of non-zeros. Number of non-zeros is just a number of ratings, and times k squared. K is the rank. So then in our implementation, we use the normal equation approach to solve the subproblems. And for non-negative matrix factorization, while we use non-negative least squares, we use projected gradient method to solve it. Basically, for each subproblem, we need kind of like a k-square storage. And we use some native C code to solve them to get a really high performance. OK, basically, that's the algorithm. And it's a very nice assumption and very nice algorithm. And paired with some application like a Netflix challenge, and it became a really popular paper. Yeah, but this is not the finishing line for us. It's because we still need to implement them, especially on a parallel system like Spark. And so the next part of my talk, I will talk about how we implement this algorithm and how we scale it up to 100 billion scale ratings. And the first thing you should consider if you implement some algorithm on Spark is the communication cost. Not every machine learning algorithms was designed for parallel system. It may work well on a single machine, but when you just translate it into a parallel system, it may be really slow just because of the communication cost. And for ALS, well, if we really want to scale up to billions of ratings, we have to store the ratings distributively, basically on different machines. And then we also need to just, if we don't make any assumptions on the input shape of the input matrix, basically number of users and number of items, we also need to distribute the user factors and basically the matrix U and the item factors. So, but then it's how we distribute the data and how we design the algorithm. And we can have this O2O. I will mention what does O2O mean here, and then block to block. This one, I put a graph here, and on the left side, this is a bipartite graph. On the left side is those users, and the right side items. And you see that we have user 1, 2, 3, and item 1, 2, 3, 4. And each edge in this graph representing a rating. And basically, for the first edge, you see the user 1 rate item 1. And so basically, if we put, let's assume that we use this O2O communication pattern. Basically, we put each vector on a separate machine. And then to solve for V1, assuming that now we are fixing the user factors. And now we are solve for V1, we need to get all the neighbors of V1. And that's U1 and U2. And assuming that they are on separate machines, we need to send the user factor U1 to the machine where V1 lives, and then the vector U2 as well. Basically, you need to shuffle. The data you need to shuffle is the number of ratings you have times the vector size, that's K. That's the number of non-zeros times K. Usually, this is a lot. Basically, think about we are considering 100 billion scale, and then with rank K, and that's about 10 terabytes of data, and you need to shuffle through the network. And it doesn't look very good. And we need to think about maybe, well, why we need to send U1 to V1 and then send U1 to V2. What if V1 and V2, and they are on the same machine? Maybe we should just only send them once to each machine. And that gave us this implementation design that's called block to block. And now I put those user factors and movie factors on separate machines. On P1, we have user factors U1 and U2. And on P2, we have U3. And then Q1 collects the V1 and V2. Now I know for vector U1, when I solve for V1, I only need to send it to Q1. And then same for U2. I only need to send it to Q1 once. And then they can use by both V1 and V2. So with this pattern, actually, we can save a lot of shuffle data. And now we give them a name here. For the blocks on the left, we call them out blocks. Basically, you are sending the vector out. You know which machine you should send it out for each vector. And for blocks on the right, we call them in blocks. Basically, those blocks are receiving the factors from the out blocks and then solve the subproblems. Yeah, so for each out block, you need to maintain a subgraph of the entire rating matrix. And in this way, the shuffle size can be significantly reduced. And if you read it carefully, you see that actually there are two directions. One is from user to item. The other one is from item to user. Well, we need to store 2 copies of the input ratings. It's not just the input, we cache it, and we start computation. Actually, it's the input, we prepare those blocks, actually store 2 copies in order to save communication during iteration. This is a very common pattern when you design parallel algorithms. And yeah, this is my favorite feature in Spark 1.4. It's the DAG visualization. And basically, when you run a job, you can go to the web UI. You can click the DAC visualization and see the entire execution. And in this way, you can see the stages on the left is the preparation stage. Basically, we are just building the blocks, user in blocks, user out blocks, and item in, item out. For the stages on the right, those are iterations. And you construct the item factor, initial item factor, you combine them with item out blocks, you filter them out, and then you join with a user in blocks and create the user factors. That's the first iteration. And you can see it for each stage, we carefully design the partitioning such that we don't do a shuffle join. We just do a normal zip join. So they stay in the same stage. So this visualization can really help you to debug your algorithm, make sure it's working correctly. And this is implemented by Andrew from Databricks. I really liked it. And next, let's talk about how to store the in blocks. Because we store 2 copies of it, we really want to optimize it. The most naive approach is just to store an array of tuples. And this user item, here is an item, user, and rating. However, well, in Java, this involves a huge overhead on storage because you need to store the reference to those tuple objects. And it's not very GC friendly. You already heard about the GC tuning. So basically, you don't want to have millions of objects inside a single JVM. You want to have a less number of objects. So then, well, let's switch to 3 primitive arrays. The first array is just item IDs, and then user IDs, then rating IDs. In this way, we only have 3 objects. Then we can really just lower down the GC pressure. And we can just, however, the issue with this one is you need to construct subproblems altogether because there is no certain ordering on the items. And for each item, you need to collect all the user factors and aggregate them. So then you have to scan over and maintain multiple copies of the subproblem. Actually have a memory requirement of nj times k squared. And nj is the number of items you have on this block. It's actually very large. Consider, well, n is maybe 100 million, and k is 10. Well, usually you may run out of memory for this. And then, well, actually we can order the items before we start the computation. In this way, we can solve subproblems one by one. And then we reduce the memory requirement from n times k squared to just k squared. And we use team sort for this because, well, usually we need to sort an array of a couple millions. And then team sort is the default sort in Java 7, and we maintain a special copy in Spark and to get a really efficient sorting algorithm. And the next thing is actually we see that in this place, we have V1, V1, V2, V2, V2. There are a lot of duplicates. Well, we only need to say, well, we have 2 V1s, and then we have 3 V2s, and then we can compress this storage. If we are familiar with sparse matrix, this is the same as a compressed row or compressed column storage. In this way, we can just easily just save a lot of storage. And then we also do a lot of optimizations here. For example, we don't do a mass lookup on the item IDs. We just remember their block ID and local indices, such that because we don't need those IDs to construct the subproblems, we only need to say, well, this is the, I need the user factor from block 1, and that's the second user factor. So we use that, and we compress those 2 information into a single integer to save shuffle data. And then we also just put a lot of specialized code to avoid garbage collection. Those codes are really nice to read, but they doesn't work for millions of items. We have to do some special thing for those code. And yeah, that's all the optimization we made. And you can see it's a long road from the paper. And we did some experiment, and this one is on the Amazon reviews data set. And it's about 6 million users, 2 million items, and 30 million ratings. And we put some stacked copy of this data set, basically just to test the scaling of this algorithm. And you see on the left is the Mahout. Basically, Mahout is was based on Hadoop, And it doesn't really work for machine learning algorithm that requires iterations. And then we have MLlib 1.2. It can scale up to 1 billion ratings. But if we want to test data sets beyond that scale, we need to do some special tuning for that. But with 1.3, with the new implementation, it's kind of very nicely and give us about 4x at very large scale. And this is the storage comparison. You can see we almost save about 4x on the storage compared between 1.2 and 1.3. And we also tested on Spotify dataset. Spotify has over 75 million users and 30 million songs. And with help from Chris Johnson and Anders and their engineers from Spotify, we run the new ALS implementation on a subset of Spotify's dataset. It's about 50 million users, 5 million songs, and 50 billion ratings. And with a 32-node cluster, we can finish the 10 iterations in just 1 hour. It's like a 10 minutes for prepared blocks and 5 minutes per iteration. Basically, if we use Spot instance, it only costs us about $10 for this computation. I think if we can make good recommendations, Spotify can easily get this $10 back. Yeah, let's recap. Basically, for the implementation, we really want to save communication, and we even duplicate the data to achieve that. And we want to use efficient storage format, and we want to really watch out for GC. And then we use native C routines to get high performance linear algebra operations. And for the future, and first thing, you notice that we put some specialized code to avoid GC. Actually, well, with Project Tungsten, we can take leverage on the implementation there and save us from those specialized code. We only need to say, well, let's do aggregate by key, and Project Tungsten knows how to optimize it. And that will be very nice for us for maintenance purposes, also for performance. And the second thing is we want to solve issues with really popular items. And those basically make a very dense communication pattern in your graph. And we also want to explore other recommendation algorithms like factorization machine. You can put in your user features and item features into this recommendation algorithm. OK, I think that's my talk. Questions?
This is on. For the 100 billion ratings, what rank did you use?
For what ratings?
I mean, sir, for 100 billion ratings.
Oh, we use rank 10.
What rank did you use?
We use rank 10.
10?
Yes.
Do you feel that's sufficient for accuracy?
No, actually, I didn't. I just tested for performance. And we also, I think we also ran rank 20. But we didn't check the evaluation result.
What size do you recommend for that scale?
I don't really know for Spotify's data sets, but for other data sets, I really just want to do a cross-validation. Usually, I found some ranks between 10 and 20 should be sufficient.
OK, thank you.
So the implementation of ALS and Spark takes 3 parameters, right? It's user ID, item ID, and
yes.
review, or the rating.
Yes.
Is there any plans to open it up so you can process a different matrix?
Yeah, I mentioned that we want to just explore maybe the factorization machine. In that one, you don't just input the ratings. You also input user features and item features. And you can incorporate those into your recommendation algorithm.
OK.
Hi, just want to ask you how to estimate the amount of memory that Spark need for running an ALS. You said it's proportional to k squared, but what is the coefficient in front of it?
That depends on your data. And for example, if you have a really dense graph, the user out blocks and item out blocks will be larger than normal. I would recommend just starting from a subset of your data set and then see how much memory you need by looking at Spark Web UI. And then just maybe scale up a little bit and see the pattern. It's very easy to calculate the upper bound, but you need to look at you need to run on real data to see the real numbers.
Okay, so which part of the data goes into the storage part and which part goes into the overhead?
For the new implementation, actually, the overhead is just we need to store 2 copies of the data. And rather than that, the implementation itself is very efficient. I don't think there are any other, just something like a Java storage overhead.
Okay, thank you.
OK, thank you.